Ladies and gentlemen, today I'd like to tell you about energy. Energy is pretty important. When we think about energy, it is that property of stuff that allows us to get work done. We're going to have to define work here in a little bit, but I think you agree that pushing a car down a road would take some work, right, on our part or the engine's part, something, right? So energy lets us do work. Work can generate energy. The two go back and forth. The picture you're looking at has surface of the sun here and some of the coronal discharge and stuff that fascinating stuff, but just tons and tons of energy up on the sun. And so let's think about energy and work here for a second. When we define work, it simply means using a force to move an object. So the symbol for work would be this capital W, and work again, force, got to move this thing some distance. So force times distance. F would be force, S is for distance, and that's all you got to do. You multiply the two. Let's say that we are using 20 pounds of force, F, and I move something 6 feet. That would be my distance, S. So how much work did I do? Well, 20 pounds times 6 feet would be 20 times 6, 120 foot-pounds. Now those are imperial units, right? Those would be the English units. They're foot-pounds. If you want to do it in metric system, then I'm going to have a unit called a newton here that we've seen before. And a newton times a meter would be this joule. A newton meter is a joule. So that would be the units there. But either way you want to do it, it works fine. This last part here, MGS, if I'm lifting an object, then that would be putting the force straight up into the air. So the force that I would have to use would be equal to the mass of the object times its gravity, right? The acceleration due to gravity there. That's how hard I would have to lift. I'd essentially have to lift its weight. And you may remember that M times G was weight. So here's the weight of the object, the force I have to use. There's the distance, and that would work. The example here follows that. How much work does it take to lift? And that's that operative word there when you use the second part. A 200 kilogram box 3 meters into the air. All right, 200 kilograms would be the mass. G, that's a constant, 9.8 meters per second squared. And the distance would be 3 meters. So if you multiply those three numbers, you come up with this number, 5,880 joules. And again, there's a kilogram meter per second squared. That much makes a newton. Newton times meter makes a joule. Power is how fast we're doing work. If I carry a box of books up the stairs here in the building, then I could do that real slow and it wouldn't take a whole lot of power. It wouldn't wear me out too bad. But if I run up the stairs, then I'm going to feel pretty winded at the top. So if I take the amount of work that I do, divide that by how long, how much time it takes, then I end up with this thing called power. And with the example that we just did, lifting a 200 kilogram mass up 3 meters, here again the work, 200 times 9.8 times 3, that was 5,880. That's the MGS there for work. But now I'm doing this in 30 seconds time. So divide by the time, divided by 30 would be 196, and that would be joules per second. A joule per second is defined to be a watt. So every time you look at the top of a light bulb and it says 100 watts, that's a measurement of power. It's how fast you're using up electricity to make that light run. You're using 100 joules every second. And somewhere in the world, somebody or something has to turn a generator and do 100 joules of work every second to get that 100 watts. Right here, another lifting problem. I don't know that we really need this, but I'll put it in here. This is kind of like problem 523 in the homework. So when you start doing these things, kind of look back at the examples that they do in the book. Mr. Beiser works lots and lots of good example problems for you. Power is work over time. Work is force times distance. And the force that I have to apply here is mass times gravity. So if I take mass times gravity times distance, that gives me work. Divide that by time, I'd get the power. This particular one here is 60 kilograms. We're lifting at 3 meters. So those are the numbers that I'm putting in. It takes 10 seconds to do that. Work it out, 176 watts. Okay. Here's one with English units, imperial units. Here the unit of force would be pounds. I got a 50-pound box. We'll say I want to lift it 16 feet up into the air. So I can multiply those two and get the work. I still need to divide by time right there. So when you do this thing out, 80 foot-pounds per second. Now there is another unit that works with for power with the imperial units. It's the horsepower. So instead of leaving this thing in foot-pounds per second or pound-feet per second, whatever, there's a little conversion here in blue that says that if once I get 550 foot-pounds per second, that's the same thing as 1 horsepower. And I can just use that like a conversion factor like you see here. You got foot-pounds per second you'd like to cancel out, put that up on top. Right here's foot-pounds per second on the bottom, foot-pounds per second on the top, cancel foot-pounds per second on the bottom, and that 550 there tells me I need to divide. So 80 foot-pounds per second is the same thing as 0.15 horsepower. All right. I think there's a problem that asks you to get to horsepower, so that's what you'd need to do there. Now, energy, we said, was the ability to do work. So if I take a moving object, something that's already moving, a car going down the road, a baseball that's moving toward the batter, whatever, that thing has mass and it has velocity. In order to get that object moving, somebody had to do some work, right? The pitcher had to throw, had to move his arm. The engine of the car had to do that work, whatever. So the work's already been done, and now that work was converted into energy, the moving energy, the kinetic energy of that object. And so KE for kinetic energy is equal to 1/2 mv squared. That's not really a derivation of it, but we'll leave it at that. This is the definition of it, so we'll go with that. M is the mass of the object, V is the velocity. I think you can see that if you had a tractor trailer, or if you had a little Geo, some kind of little car, it's going to take a different amount of kinetic energy. Those will have different kinetic energies because of the mass. A monster truck going down the road, a lot of mass, a lot of kinetic energy. If it's just a little car or a BB or a spitball or something, little bitty mass, little bitty kinetic energy. So those go together. The velocity also matters here. And I guess you could ask the question, do you want to get hit by a book that's moving slow or a book that's moving fast? Well, the right answer is neither one, right? But if you got to pick one, you're going to take the slow one. Somebody throws a book real slow, that's better than getting hit fast. So the velocity is also important in the kinetic energy here. In fact, it's so important that it has to be squared. We have to put that factor in there twice. So here's an example. Calculate the kinetic energy of a car that has a mass of 1,500 kilograms. It's moving at a speed of 5 meters per second. We're reading the numbers right there, 1,500 kilograms. That's the mass. So I write that down. M equals 1,500 kilograms. Over here, the speed, the V, 5 meters per second. So I've got that number. I just slip them into the formula here and punch it up. 18,750 joules. Watch the units here. This is a kilogram. This meter per second gets squared, so I got 2 meters in 2 seconds. If I take the kilogram and one of the meters in both seconds, that'd be a kilogram meter per second squared, which is a newton. Got one more meter left over, so a newton meter would be a joule. I don't really care if you know how to get the units worked out of this, but they do work, and they will tell you if you're doing the problem right or not. So kind of keep an eye on them. Here's another kind of energy right here, the potential energy. And this is the energy an object develops by being raised to a height. If I have a calculator sitting on my desk and I lift that thing up, right? I move it up into the air and I hold it up there in the air. It took some work to lift it, right? So the work that I did now gets stored as potential energy. It's not moving, so there's no kinetic energy. I'm just holding it there. But it has potential energy. It has the potential to develop kinetic energy. If I turn loose of it, the thing starts moving, right? So the work that I did got stored as potential energy, and that can get converted to kinetic energy when I turn loose of the object. The formula here for the potential energy is simply mass times gravity times height. The bigger the mass is, the more potential energy it's going to have. The higher up in the air, the faster it can get moving, the more kinetic energy. And of course, G is there because gravity is what's pulling on the object, accelerating it. Here's an example. Find the potential energy of a book that has a mass of 5 kilograms. It's 2 meters above the ground. So those are our two numbers, M and H or S, either one. You'd put them into your formula here, punch it up, 98 joules. Okay? Kilogram meter per second squared is a Newton times a meter would make a joule. Now, energy is interesting. You can't create it. You cannot get rid of it. All you can do is move it from one form to another. We call this the law of conservation of energy. And another way of saying it is that the total energy of a system cannot change unless energy is taken from or added to the system. And if you pick any 2 points, the top of the hill, the bottom of the hill, on the roof and down on the ground if you drop a hammer, any 2 points you want to think about, mile marker 79 and mile marker 77 on Highway 77, whatever it is, the energy has to be the same at those 2 points unless you take energy away or add energy to it. When you want your car to go, if it's sitting there, you have to put some energy in it. The energy comes from the gasoline, right? There's chemical energy there, and when we burn it, it becomes thermal energy, and the thermal energy turns turns the motor, and so now it's kinetic energy, and that kinetic energy goes through the drive shaft and turns the wheels of our car, and our car moves, and that's kinetic energy. It changes from form to form to form, but I cannot create energy out of nothing. I have to add to my gas tank every now and then, and the brakes take energy away. They stop it. Air resistance takes energy away, but that energy goes into the brakes, right? The brake pads get hot, and the air resistance causes wind to come off of the car and stuff. So all of the energy is still there. Nothing is ever lost. Nothing is ever created out of nothing. But this conservation of energy is a big deal in physics, and so that's why we wanted to say something about it here. This is a little formula version of it. If you took the potential energy at one point and the kinetic energy at that same point and added those two together, that would be the total energy there, right? How much potential energy, how much kinetic energy, add those up. It's got to be equal to the potential energy plus the kinetic energy at some other point, at some other time, later on down the road. This sum has to equal that sum. A good example of this would be a roller coaster, right? You're up at the top of the hill of the roller coaster. You're moving very, very slow. So you have very small kinetic energy, but you're way up in the air, so you got lots of potential energy, right? When you add those together, you'll get a number. Let's pretend that you roll on down the hill now. You can scream if you like. Nobody's listening. And you get moving very fast, so you've got lots of this, but you've lost all that height. You traded in your potential energy to get kinetic energy. And so this is down, but that's up. And when you add these two together at point 2, you get the same number that you had at point 1. If you start to go back up a hill, you're going to lose kinetic energy, but now you're higher in the sky, so you're going to gain potential energy, and it stays constant. The total energy is constant. Here's a couple little pictures that might help. Let's say there's a house here, and I stand on the roof of this house, and I've got a hammer in my hand. I could use the potential energy formula and find out how much potential energy there is. And I just made up a number. Let's say it's 20 joules, right? I've got 20 joules of potential energy because it has the potential, if I turn loose of it, to develop kinetic energy. If I drop this hammer that has 20 joules of potential energy, when it hits the ground, all of that potential energy is gone. Potential energy is mgh. Well, there is no h down here, right? So the question is, where did the potential energy go? The thing is moving very fast just before it hits the ground, so it's got lots and lots of kinetic energy, and it should have 20 joules of kinetic energy there. So the number is the same. At the top, at the bottom, I got 20 joules. If you pick any point along the way, let's say this one, I have lost some of my potential energy because I'm down lower now. I might be down to 15 joules, but I've picked up some speed. So that would be the other 5 joules that I'm missing. Again, 15 plus 5 is 20. That same 20 that I have here. By the time it gets way down here, I'm down to 3 joules of potential energy, but I've got a lot of speed. I've got 17 joules of kinetic energy. So it works out just fine. All of these formulas, none of them are really hard. The hard part is to keep them straight and to figure out which one to use when. So you're looking for some key words. They will either say find the kinetic energy, find the energy of that moving object. In that case, you're going to use Ke equals 1/2 mv squared. They might say find the potential energy. So here's the formula. They might say find the work if I use this force over a certain distance. There's a formula. Conservation of energy, I won't ask you to do problems with that. That involves a little bit of algebra, and we don't need to go that deep. But we've seen that. If they say, give me the power, we got a formula for power. So the whole game here is organization. It's trying to keep these formulas, these quantities isolated and separated and understand what the parts and the pieces are. If you can get everything on a table like this one, right, where it reminds you that kinetic energy is the energy of a moving object, here's the symbol and there's the formula, it ought to come out in these units, then that's half the battle right there. All you got to do is just grab the right formula and put some numbers in after that. On this first test and on the second test as well, you may bring a 3x5 index card. Maybe you want something that looks like this table so that when you go down to the assessment center and get your test, you can have that for reference, right? But that's up to you. You can put whatever you like there on the card, but these formulas are pretty important, and I don't really expect you to memorize them all. If you looked at all the formulas that we've had, it would look something like this. Here's the formulas out of Chapter 2, and here's the ones out of Chapter 3. We didn't do Chapter 4, but here's Chapter 5, right? So if your note card looks something like that, and you saw a question that said, give me the acceleration, you'd start looking for a formula. Here it is right there, and you could put in the numbers. Or if you needed to know the power, right? Somehow organize these ideas so that you can recall them. All right. Thank you much.